what time is it?
Huh? It's Gibbs o'clock.
You know what Jarvis said, if we don't know Gibbs by Monday, oh boy, you better not show up for class, Jack.
Wait, I don't know Gibbs. But I know who to ask.
Wait, Jack, I know Gibbs for energy. Check it out. Gibbs free energy.
I don't know the first thing about Gibbs free energy. Can you give me some background?
Jack, luckily I know a whole bunch about Gibbs free energy. Gibbs free energy was a term developed by Josiah Willard Gibbs in 1870. It is known as the available energy of a system or the thermodynamic potential, which can be used to calculate the maximum reversible work. Gibbs can be used in so many ways. The one way is to predict the direction of a reaction at constant temperature and constant pressure.
Dylan, I want to need some more details than that. Let's get down to the nitty-gritty. Let's do some equations.
That equation up there is the bread and butter for Gibbs free energy. It's defined as delta G equals delta H minus T delta S. Delta H is equal to enthalpy. Enthalpy is the measurement of energy inside a system. Delta S is the entropy. Entropy is essentially the dissociation of a system. Imagine I have a bowl of nuts all together, and I throw those nuts all around the room. That's increasing the entropy. T is temperature, and that is mainly used in Kelvin.
So I get the equation, but how can this be used in a reaction?
Gibbs free energy can be used to determine the direction of a reaction. If delta G is negative, that means the reaction is spontaneous or exergonic, which means it gives off energy. If delta G is positive, that means it's spontaneous in the reverse direction. That means that the reaction is endergonic and it takes in energy. If delta G is equal to 0, that means the reaction is at equilibrium, where the forward rates of reaction are equal to the reverse rates of reaction. If delta H is positive and delta S is negative, that means that Gibbs free energy will be positive at all temperatures. If delta H is negative and delta S is positive, that means that delta G will be negative at all temperatures. If delta H is positive and delta S is positive, that means at low temperature it'll be positive, and at high temperatures Gibbs will be negative. If delta H is negative and delta S is negative, at low temperatures Gibbs will be negative, and at high temperatures Gibbs will be positive.
Wait, so I have a question. Is Gibbs free energy a state function?
Good question, Jack. Yes, you're right. Gibbs free energy is a state function. This means that the delta G is only the difference between the initial and final energy states. That also means that delta G is independent of path or mechanism taken. That means that delta G cannot tell you anything about the rate of the reaction.
So Dr. Jarvis mentioned something about Gibbs and equilibrium. You know anything about that?
Gibbs free energy can also be used to examine reactions at equilibrium. The equation that we're going to use is delta G equals delta G standard plus RT natural log of Q. Delta G is the Gibbs free energy. Delta G standard is the Gibbs free energy at standard state. R is the gas constant. T is the temperature at equilibrium. And natural log of Q is the natural log of the reaction quotient. At equilibrium, delta G is equal to 0. That means that the reaction quotient is equal to the equilibrium constant. 0 is plugged into the equation and rearranged to get delta G standard state is equal to negative RT natural log of the equilibrium constant. As you can see here, the equilibrium constant is the concentration of the products over the reactants.
Wow, Dylan, that was very informative. Thanks for that. I just need to go home and do some practice problems, and I know I'll be ready for the test on Monday.
Hey, how'd class go, Brohim?
I think it went pretty well.
Yeah, nice.